First, I have to doff my hat to the magnanimity of the IEEE. See, what Thelma couldn't bring herself, essentially, to tell you is that I'm a professor of mechanical engineering. Okay. And I think it's a happy commentary on fairness doctrines. You know, fairness doctrines are an important dimension of our political 1984 year. I think it's a happy commentary on the fairness doctrine of the IEEE that they'll let a mechanical engineer get to the podium. But I think it has a kind of a implicit message, which I have no problem with whatsoever. We interact with the physical world. We transduce information from the physical world largely mechanically. And when we want to interact with the physical world, we push and pull and move it around mechanically. But if you want to process the information in between, there's no way to do it but with electronics. And in fact, the chip and the computer essentially are in fact eroding the areas that the mechanical engineer used to occupy at both the information acquisition end and at the movement end, basically. But we'll always have a stake, essentially, because of that physical interaction we have with the world. I wanted to put my remarks into context, particularly following the discussion this morning on electronics and defense. I want to give you a couple of scalars to get you properly situated to discuss electronics in rehabilitation of humans. Let me first give you, I don't have time to develop any of these things in detail. I have given the IEEE people some reprints, which I understand they've copied, and if you're interested, some of these topics can be developed in more detail in those reprints. In particular, a reprint from Technology Review develops some of the characteristics of the handicapped population and of the response, essentially, of both of the medical and rehabilitation communities to the problems of handicapping conditions. In a word, at least 10% of Americans are seriously handicapped. So you're talking about 25 million people, basically, a whole range of different kinds of disabilities, but nevertheless a very, very large population. Let me counterpose the scale of the problem with and I'll narrow myself to the federal financial response by noting that I have it on the authority of Dr. Leo Young that the current federal DoD budget for R&D, primarily, is $30 billion. Okay? Remember that number. The handicapping conditions are irreversible losses that humans experience, usually following some medical episode. It could be congenital, it could be disease, it could be traumatic. But as I develop further in this Technology Review article, medicine doesn't figure very centrally at all in the rehabilitation scene. It's a very, very modest component in the rehabilitation scene. So I want to now counterpose the investment we make as a country into medical research, which for a minute I will not deny the Tom Budingers of this world. I expect to benefit by the kinds of research that he has been just demonstrating, but I want to counterpose that against research and development for handicapped persons in particular. The typical annual budget of the National Institutes of Health that address disease and medical attack on disease and other dramatic, life-threatening human maladies is typically $4 billion. So it's roughly 10% of the DoD R&D budget. So I guess health is worth 10% what defense is, if you will, if you want to use that kind of a very, very crude metric. What's the investment of the federal government in handicapping conditions? Well, there's a National Institute for Handicapped Research, not part of NIH, and its annual budget is typically $30 million. If you add what the VA and NSF do, you're up to maybe $40 million. So handicapping conditions are worth 1% of what we invest in health and 1/10 of 1% of what we invest in defense, normalized against research. Okay? So, a large population and a very modest response.
I'm going to bring you a rather different message than you've heard from the previous two speakers. And the basis for the message that I'm bringing you is the computer revolution that is taking place today. Any of you who have recently bought personal computers are well aware of the kind of revolution that is taking place. And it means that the future is genuinely different from the past. And what you've heard from the previous speakers is the supercomputer problem as it is developed from the past. But I agree that we are in a supercomputer race with Japan, but I want to focus attention on the question of what do we want supercomputers for in the United States? In other words, what is our goal, and what do we do to reach that goal? But the first thing I want to say is the following, that there is a question that is in the air right now and probably will be decided certainly in the next few months, perhaps in the next few weeks. And the question is, do we as a country move ahead rapidly, incur lots of risks to try to reach the goal that I will discuss, or do we go slowly? Do we measure every step? Do we take time to correct mistakes? Unfortunately, the situation at present is that there are a number of people, myself included, who are ready to go on the fast track on this issue. And we have already started projects that assume that the fast track is going to develop, that assumes that the country is going to back a major push forward in supercomputers. So there are projects at Cornell, there are projects at the University of Illinois, there are projects inside the computing industry, which I obviously have to be very careful about discussing. There are projects I see in every visit that I've made to industrial users of computing. There are projects there that cannot succeed unless supercomputers are supplied to the industries I visited. So there's a community of people in industry, in universities, and in government that are ready to move, are already moving, but they need a signal that they're going to be backed. And I will come later to what that signal has to be. And as I said, that signal, if it comes, is in the next few months. And if that signal does not come, it will be, the efforts that are now underway will collapse, and it will take several years to recover the momentum that is now developing. What is our goal, the goal for the U.S. in working with supercomputers? I believe the goal is to expand the creativity of the U.S. economy. I am talking about this kind of creativity which we are celebrating here today, the creativity which produced the light bulb, the telegraph, the transistor, the optical fiber, the fantastic discoveries which our entire economy depends on. Building the creativity of our economy for the future is, in my view, more important than questions of tax policy, trade policy, dealing with a deficit, struggling with all the stupidities that go on in this town. And I remind you that underlying all these problems is we have problems, and so does Japan, that of trying to support Social Security, Medicaid, defense. And we have to strengthen our economy as we have never done before to deal with those issues. And that's independent of who's in office here in Washington. But that's not the only issue. The other issue is, with supercomputers, as I will discuss, we can make life more exciting, more interesting. And that's one of the reasons I'm here today.
See, I'm not quite sure why I'm on this agenda with you folks this afternoon. Defense is a prolific user of computers, almost none of which are supercomputers. There's a long and involved history of why that situation obtains, and I won't bore you with the details of it, but basically, aside from the computers that are used in the Department of Energy laboratories to design nuclear weapons, which I guess you could consider a defense application, although they perhaps better belong to the Department of Offense rather than the Department of Defense. And aside from the certain use of machines by the intelligence community, particularly the National Security Agency, which does serve defense purposes, about the only use for supercomputers in defense per se is in numerical weather forecasting and in certain aeronautical research, which is done by and for defense. And I don't foresee in the near future that situation will change much, but there is a crying need for advanced computer capabilities in defense, and is the basis for a new program that was started by ARPA during this past year. And that particular thrust is typical of the kind of thrust that you will find ARPA making, which is to try to project 10 years into the future, not to look at the near-term horizons that are required by the researchers in industry, required of their marketing and of their general management, but instead to look beyond, to look at the needs for defense computation in the decade, beyond the decade in which we now exist. Basically, what is that need? As we see it in defense, the need will be for an ability to create computers which can essentially magnify the power of both strategic and tactical weapon systems of that era. The reason is clear, and that is because our adversaries, particularly those in the Warsaw Pact, are outspending us by substantial sums in every major weapon system area. And by and large, the capability of the weapon systems being produced in the Soviet Union is increasing and is increasingly comparable in their very capability to our weapon systems of today. So we will find ourselves, if we project into the 1990s, in a particularly poor adversarial position with respect to the Soviet Union. They will have capable systems in numbers far superior to the numbers of our systems. Consequently, the feeling is that the only way that we can deal with that problem is to build the capability of our systems substantially. And the power of our systems, the complexity of those systems, will demand a new kind of computer be created. Now, those computers, I suppose you will be able to call them supercomputers, but perhaps they would be better called super intelligent computers. And the thrust of ARPA's research program, which will be substantial, is probably more comparable to the Japanese fifth generation program, of which Sid Fernbach spoke briefly in his opening remarks, because it will create a new genre of computers that will be able to emulate human thought and be able to help us to control the very complex weapon systems of the 1990s era. It will make it possible for us, hopefully, to magnify the capability of those systems to the point where they will be effective, many for one, in an engagement with the more conventional weapons which will be fielded by our adversaries in that time period.
It's time for questions. Yes.
For Dr. Cooper, do you see any applications of supercomputers in the space defense system being developed, particularly in the command and control aspects?
Yes, as a matter of fact, when we created this program during the 1982 year, calendar year, the battle management problem that we selected was selected without benefit of the President's speech of last March 23rd, where he advocated defense research on ballistic missile defense. Since that time, we've looked carefully at the possible contributions that machine intelligence may make to a 1990s era space defense system, and we feel that machine intelligence may well be an enabling technology for ballistic missile defense. That is, without success in this area, the complex interactions in a ballistic missile defense scenario may well not be controllable. The number of elements of the defense system, the complexity of the offensive capability of our adversaries, plus all of the junk and penetration aids that one might expect in such a battle would certainly preclude human control of such a battle as it evolves over maybe a 10 or 15-minute period of time. So consequently, much of the activity is going to have to be under intelligent control of intelligent machines.
Thank you, Dick. I was struck this morning when I was listening to one of the speakers on electric power by a comment that he made saying that the last 10 years is a relatively short time to get any predictions or trends. And the second thing which struck me was the motto over here, a century of electrical progress, and putting that into the telecommunications field, all that happened in the last 10 years. Sort of in the telecommunications field, a lifetime has been lived both by the individual participants and by the technology in just the last decade. I think the most important part of what I'm going to be saying is that if you take away the divestiture, and if it had never happened, the field would have been heading towards chaos and crisis. There are many, many different pieces of evidence that point to that. When you add the divestiture on top of that, the potential chaos in the field just accelerates. And what I'm going to be doing this morning is stepping through some of the things which lead me to that conclusion. I'm also going to hope to suggest a few ways that we might avoid it, but I think that all of the steps that are needed to create this crisis are already in place, and it will take Herculean efforts to avoid that.